Well, thank you all very much for coming. So, as the title suggests, I'm going to talk to you about the topic of phase transitions, and in particular, their manifestations in the quantum world. And so, in this first section of the talk, I'm going to speak about examples of phase transitions that you're probably all aware of, and with the aim of trying to show you what are the essential elements of a phase transition. And so I want to apologize a little bit for my first example. I wrote this talk during the Christmas holidays, and with the speed of things that have happened in the last 2 months, some of you may find this example distasteful, in which case I apologize, and perhaps you can not pay attention during the first few slides. Okay, and so without further ado, you are no doubt a little surprised to come to a physics talk and see that the first slide is a discussion about the circumstances of the beginning of World War I. So as the reproduction here from this Italian newspaper suggests, assassination of Archduke Franz Ferdinand, the heir presumptive of the Austro-Hungarian Empire, and Sophie, his wife, the Duchess of Hohenberg, were assassinated at the end of June in 1914. And so they were both in town in Sarajevo, checking on the military installations there. And after having lunch at the town hall, they joined their motorcade. And through some series of events, got separated from their motorcade. And worse yet, the chauffeur of the car literally stalled in front of the assassin, who was a Serbian nationalist who was protesting the Austro-Hungarian rule of Serbia. And so this act is generally believed to have been the one that triggered World War I. And I'd like to at least use this example to demonstrate some of the essential elements of phase transition. And so the elements of a phase transition are described here. And the first one is that there has to be a before and an after. Some quantifiable system-wide change has to occur during a phase transition. And indeed, World War I was a turning point for Europe and the rest of the world. In addition, complex systems of all kinds often have competing forces in them. And they make possible instabilities, but they don't make instabilities a guarantee. And these are some of the forces that were present in the run-up to World War I. The most important feature, I would say, for a phase transition is that as you approach the phase transition, the number of possible outcomes gets fewer and fewer. And so, as you can tell from this map that I reproduced over here, you can see that there were empires that sort of segregated Europe into different groups, and it is in fact the network of mutual assistance treaties among those empires that had accrued over the previous 100 years, which was actually the limiting feature that led to a possible phase transition. And if you see where Serbia is, which is where this event happened, it's unlikely that anything could happen in Serbia that would escape the notice of either the Russian or the Austro-Hungarian empires. And so, indeed, a triggering event happened in Serbia. So you are free to disagree with my interpretation of history. I'm fine with that. But I think that there are these 4 elements of phase transitions that you'll see over and over again in other settings. So the next page is sort of a different take on it, which is evolution could also be considered a sequence of phase transitions. And as an example of that, I think a number of you will know about the Galapagos Islands and the uniqueness of their environment. They are a self-contained environment. And so these 2 scientists, Peter and Rosemary Grant, studied the small birds, finches, that lived on the Galapagos Islands. And their work is related in their book, The Beak of the Finch. And so Evolution involves environmental forces and competition among species as sort of driving forces. And in this case, one could say that in 1977 there was a drought which triggered a change in the ecosystem. So because of the drought, the food became less abundant, and what was retained were large and hard seeds. And so birds that had strong beaks were able to eat this food, while the birds with smaller beaks were not able to, and so many of them died. And so you could imagine that that is also sort of a fork in the road for the finches. So another example of a possible phase transition. However, being here in Aspen, I think it would be inappropriate of me not to mention perhaps the most ubiquitous of phase transitions that happen around us. Those are the phase changes that happen in water. And so I'm using this example to introduce to you an idea that I'll use over and over again in this talk, which is that there are, of course, 3 phases of water. And I've organized them here in what's called a phase diagram, which is this is pressure and this is temperature. And you can see that the different colors are the 3 phases. There's vapor, liquid, and solid. And it is straightforward to identify a phase transition in the water system due to the mechanical differences in the mechanical properties of water. You can always tell liquid and solid water apart. And so you may be interested to know that there are more than 20 different forms of ice that are known as functions of temperature and pressure, and they're indicated here. The one that we mostly see is this hexagonal form, which is present at low temperatures and at ambient pressure. But it is, in fact, not the only form of ice that you would potentially see here in Aspen. For those who are literarily inclined, I've also pointed out Ice 9. So far, no problem. It's a high-pressure phase of ice, but seems to be pretty stable. And I guess that's what I have to say about solid ice. But the point I want to make also is that phase transitions also have signatures in terms of behavior, in terms of length scales and time scales. And so let me talk to you a little bit about that point. So as these panels up here on the upper left represent, they are meant to represent the lead up to a freezing of ice. And so if you're well above the freezing point of ice, you will have water in blue and you will have ice in red. The pieces of ice may be very small. They may be microscopic. And they are also ephemeral in the sense that they're coming and going as they exchange energy, heat energy, with their environment. However, as you lower the temperature, the regions of ice get larger, and their dynamics become slower. They're longer lived until eventually, at the freeze up, you can walk from one side of your body of water to the other side without getting your feet wet. The ice spans the water, and it's long lived. It's there for long time periods once it has frozen. To give you an example of this, at the right, I'm showing you some information about a place in Nunavut, which is in the north of Canada, called Peel Sound. And it's indicated here in these 2 Arctic maps, as you can see. And so here's a picture that was taken in October 2024. There's no ice in Peel Sound at this point. Peel Sound is a large body of water, hundreds of miles in extent. Just a month later, it is completely frozen. 1 month to go from here to here. And to give you an idea about the progression of that freezing, these are ice maps that you can get from this amazing website, which I highly recommend to you. And you can see that we have open water here in October, but it's totally frozen in a month later. And for your convenience, this is the length scale that is involved. And so that gives you some idea about those dynamics. So of course, everything that I've said up to this point suggests that these phase transitions, this change from water to ice, happens instantaneously. But that's a bit of an overstatement. I want to show you just a fun video that will demonstrate this to you. So just water. I love that. Well, I love that one even better. So what's really happening here is that the water is actually colder than 32 degrees Fahrenheit. And so there are little crystallites that form on the bottle, and they serve as little seeds for the ice to nucleate around them. And then there's sort of an explosive kind of crystallization that happens as you saw in this video. The extent to which that happens in nature, I'm afraid I don't know. So taking another step back, you may at this moment be thinking that phase transitions are something that happen at low temperatures. But I hope that this phase diagram will dissuade you of that feeling. So this is a temperature density phase diagram, and the temperature here is in trillions of degrees. And so this is a scenario that happened in the early universe. And at a certain point, there were quarks that were running around just being quarks. And eventually, as the temperature dropped below a certain point, the quarks were bound together by strong interactions and became hadronic matter, things like protons and neutrons. And so, of course, that was a very important part of our history. And so the reason that I mentioned this to you is to emphasize the point that phase transitions have this property of universality, which is it doesn't matter what temperatures we're talking about. Details of the system, to a great extent, don't matter as well. That the overall phenomenology, the characteristics of the phase transition itself are the same in all of these systems. So here's my favorite system for studying phase transitions in. And it's meant to be a very simple model of a very complicated system, which is a metal. So inside the metal, you have the positively charged cores of the atoms, and the blue is meant to represent the unbound electrons that can move anywhere within the metal. And those are the ones that are responsible for carrying electricity and heat, for instance. And so these electrons, of course, are negatively charged, and so they tend to repel each other due to that charge. So I'm going to invite you to do a thought experiment, which I'm describing to you here. So imagine I have these little pieces of space. They're very small, and I want you to take a pair of tweezers and put electrons into the space one at a time. And so as you put in the first electrons, you'll see that because the electrons repel each other, they're going to go as mutually far apart as they can go inside this space. And so they're going to go far apart. So as you increase the number of electrons, however, you can see that the electrons are becoming screened by all the other electrons until eventually, when you have a lot of electrons in there, the system is actually transformed into a fluid of electrons. The electrons can flow anywhere that they want inside the system, which is very different to where you started. So here's the temperature density phase diagram of this system. And at low densities, what you find is that you have a crystallization, or the electrons are localized on certain spots in this space, and that above a certain density, however, they become this unpolarized fluid, a regular, like a fluid of electrons that can move freely. So in putting this talk together, you may imagine that I might have been influenced by this gentleman who is David Pines. I ran across this a statement that he had made about emergence as being a phenomenon that is typical of complex systems. By emergence, I mostly mean something like the whole is better than is more than the sum of the parts. So in the remainder of the talk, I will try to make the case that phase transitions are one set of language in which we might try to understand that complexity. So David Pines, of course, was a fellow resident here in Aspen to many of you, and also a longtime supporter of the Center for Physics. So now I have to actually be serious about talking about phase transitions from the point of view of physics. And so, as I've said in the last section, we know of phase transitions that happen, for instance, as we lower the temperature. And an example would be going from liquid water to solid water, or perhaps from not being magnetic to being magnetic, something like that. And so imagine the following, which is that in addition, you had some other knob that you could turn. Maybe it would be pressure, could be magnetic field, it could be the composition. And so if you apply the pressure, for instance, it could happen that this ordering temperature could happen at the ordering could happen at lower and lower temperatures. In fact, why not press it all the way to zero temperature? So this is absolutely possible. And I would say that if you were up here at high pressure and you lowered the pressure towards the ordered state, at T equals 0, this is the first time you see the ordered state. So this phase transition happens at zero temperature. I don't mean 0 Celsius, I mean 0 temperature. And so as a result, we know there's no heat that's available to drive a phase transition. This mechanism cannot be the one that happens at zero temperature. And indeed, it is the quantum fluctuations, the quantum character of the system itself, which is responsible for the transformation at T equals 0. I'm going to say more about that as the talk goes on. So I'm sure that some of you are thinking like typical physics, right? Which is you have something at zero temperature, and now you're going to tell me all about zero temperature, but you can't do experiments at zero temperature. In fact, through the work of these gentlemen, it was subsequently determined that even at quite high temperatures, you can still see evidence that you have a zero temperature phase transition. So it's sufficient for us then, when we do our experiments, to work at non-zero temperature and to deduce what the properties are at zero temperature. Next problem is it must be some very special system that we developed in our lab, and it's unstable. That's not true either, in that some of the materials that you know very well have these zero temperature phase transitions. And the example I want to share with you is this one. It's iron. So iron is something that I guess everybody in this audience has touched at one point or another. And here is the temperature-pressure phase diagram for iron. So at high temperature, iron is not magnetic. But at ambient pressure, if we lower the temperature below about 1,000 degrees Kelvin, iron becomes ferromagnetic, just as you experience it at room temperature. However, if you apply pressure, the temperature below which the magnetism exists comes down and down and down and disappears at about 12 gigapascals. That's a very large pressure. And so this phase is called alpha iron, and it's distinguished by the way that the iron atoms are put together into the crystal lattice. If you increase the pressure, the atoms are put together in a different way. This is called epsilon iron, and it's not ferromagnetic. And so at 12 gigapascals, there's a zero temperature phase transition with respect to iron. And there is some evidence even that the phenomena that are associated with that phase transition can even be seen at very high temperatures. So zero temperature phase transitions are in fact not hugely rare. And I've just to repeat what I said before, iron has a thermally driven phase transition. It also has a quantum-driven phase transition, both in the same system. Okay, so having said that there were two kinds of phase transitions, in the next two slides, I will do my best to explain to you what happens at a phase transition. And so you should feel free to stop me if there's some clarification that I can offer. So I'm going to start with this thermally driven phase transition, this one here. And I'm going to need to introduce an idea called spin. I'm not going to tell you what spin is, other than it's an intrinsic property of electrons, and it has the feature that it will align the electron with or against magnetic fields. And so there are spin up and there are spin down. So I'm going to take 5 of these spins, and I'm going to combine them in different ways. There are 32 different ways that I could do it, and here are 4 of them. Okay? And so the thing to say about this is it's definite in a classical system, whether you're in state 1, 2, 3, or 4. They exist independently of each other, but they do have different energies. Specifically, you can see that if in state 1, if you flip the spin, you'll get state 3. To do that, you have to pay the energy difference between these 2 states. So this landscape down here at the bottom is meant to represent how these states are organized. And specifically, if I said, let's put state 1 here, state 1 has to stay there because there's this energy barrier that separates it from this lower energy state, state 2. So state 1 can drop down to a lower energy and become state 2, but only if it can get some heat energy from the environment to allow it to do that. Are you guys okay with that? Okay? So you have to go over this energy barrier in a classical system in order to get into another state. So that is a feature of the classical phase transitions. So now I'll turn to the quantum phase transitions, and I'm going to use an analogy to explain this. So here are the same sets of spins as we saw on the last slide. I'm now calling them configurations for reasons that I hope could become clear in a moment. And I'm explaining this kind of phase transition where we're at 0 temperature throughout. And so the idea is that these configurations altogether will form a quantum state. And so here's the analogy. Say you want to make a curry, okay? And in this story, the curry is representing the quantum state. So you go to the market and you see all the different spices and herbs and ingredients that you could use to build a curry. And so a particular combination of these spices corresponds to a quantum state. They are the ones that you are going to use in your particular curry recipe. However, you know perfectly well from your own experiences that the overall properties of your quantum state, your curry, will vary slightly depending on the recipe that you use, right? A little bit of salt, just a small bit of difference in salt between a curry that has 50 different spices in it will make a demonstrable difference. And so the different quantum states actually are not necessarily that different from each other. Your recipe with a small variation has a huge degree of overlap with the recipe without the modification. And so the quantum states are not as to be thought of as completely separate objects, but they involve all the configurations simultaneously. They have a large degree of overlap. And so with small fluctuations, you can go from one quantum state to another quantum state. I'll let you take that in for just a second. Okay, so here's the energy landscape again. And I have 2 quantum states, 1 and 2, that are down here. And you can see that there's an energy barrier between them. But it's no problem, because these states are inherently mixed together. They overlap with each other, and they sort of tunnel underneath this energy barrier. So there's no need for them to exchange heat energy with the environment, go from state 1 to state 2. Amazing, but in fact true. And so we would say then that states 1 and 2 are entangled with each other. All right. In the next few slides, I just want to tell you how amazingly different the properties of materials are when they're near one of these 0 temperature phase transitions. So more or less, this is if you see these phenomena, then you experimentally have a good chance of being near a 0 temperature phase transition. And so here is some beautiful data from the group in Stuttgart on this material, ytterbium trichloride. So this is a temperature field phase diagram. And you can see the phase line. It terminates here at 0 temperature and 6 Tesla. And so I won't tell you all the details of this, but this is a color plot that represents the intensity of the thermal conductivity, the ability of this system to conduct heat. And you can see it's strongly enhanced near 6 Tesla, which means a special feature of quantum critical materials is they have unusual responses that aren't there for classical systems. Here's, of course, the other aspect of conductivity is the ability to conduct electricity. So here on the right is a measurement of the resistivity for a straight-up copper wire, which is, by all accounts, a conventional metal. And here on the right is something about the resistivity in this other system, ytterbium, rhodium-2, silicon-2, which is a quantum critical metal. So you can see there's the temperature field phase diagram again. And so at low fields and at high fields, this is a material that acts much as copper does in terms of its ability to transport electricity. It's copper. But right here, near the quantum critical point, there's this fan of fields and temperatures, which is orange, where there's a very different mechanism for conducting electricity. And so this is the second half of what I meant to say, which is the physics is just different near the quantum critical point. That explains why the behaviors are different. Okay. Here's perhaps my favorite part about quantum critical points, and it's demonstrated by this delightful material, cerium-indium-3. So cerium-indium-3 orders at about 10 degrees, and now we're applying pressure, and the ordering temperature comes down, 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 and just when you think it's going to form a quantum critical point, hit the axis at 0 temperature. Instead, you see this little dome of superconductivity. We love superconductivity. It's the ability of a material to conduct electricity and heat without any kind of dissipation or resistance. It's a signature of a quantum phase. And so you could think about this in a couple different ways. One could be sort of zero sum, where you would say that you have to get rid of the magnetic order to make things possible for another phase, such as superconductivity. One way to think about it. You could also think about it by saying, by reflecting on what I said in the last two view graphs, which is that the collapse of magnetic order fundamentally changed the properties of the materials near the quantum critical point. And they change it in such a way that it makes another phase, superconductivity, possible. This actually turns out to be quite a common phenomenon and independent of the class of materials that you think about. And so if we start here with the cerium-indium-3, this is a particular class of materials. But here we have a phase diagram, temperature, pressure for another class of materials, another one, another one. And I think that if you look at these phase diagrams, you can see that they're quite complex. You have magnetic states, you have superconducting states, and in all of them, you have a quantum critical point, a zero temperature phase transition, which controls the phase properties of these systems. Okay, so want to take just a moment to take stock of what I've talked about so far, which is that we have these zero temperature phase transitions, that we can detect their properties at higher temperatures. And so these materials are important to us because they are a rich and ready source of quantum states. There are many of them, and they dominate the behavior for a wide range of temperatures and, say, pressures. And the question, I think, that I want to now address is, how is it that those quantum states result in the properties that we see around the quantum critical points? And the suggestion, let us say, that I want to make is that correlated materials, or the properties of the materials near these quantum critical points, will give us a new way to look at the fundamental quantum physics of matter. Okay? So a very humble statement on my part. So the most fundamental aspect, I would say, of quantum matter is this issue of entanglement. And I haven't explained it to you just yet, but I'm going to let these two eminent scientists, Albert and Marie, do the explaining for me. So they're hanging around the lab on an afternoon after lunch, and they're listlessly flipping coins, as one does. And so Albert flips his coin 10 times, and about half the time he gets heads and half the time he gets tails. Okay? This could happen to you. You could do this right now if you had a coin in your pocket. At the same time, Marie is doing the same thing, and she also gets 50% heads, 50% tails. She has a different sequence of heads and tails from what Albert had. Still, these are regular coins. This is your regular real-life experience. And so whatever happens to Albert with the heads and tails is independent of what happens to Marie. These are completely uncorrelated events. Good? Good. So Marie says, no, I was busy in the lab last week. And so she walks over to a drawer, and she comes back with 2 other coins. And she gives one to Albert, and she keeps one for herself. She says, these are special coins. And in fact, they are. And so she says, go ahead, Albert, flip your coin. And he does, and he gets a head. Marie looks down at the coin in her hand, and she says, it's a tail. Okay, that is not so exciting. She said, try it again. And so this time he gets a tail. Marie gets the head. Still not so convincing. They do it 100 times. 100% of the time, whatever Albert gets, Marie gets the opposite. 100% of the time. 99%, 100%. So you cannot say that these outcomes are completely independent anymore. This is a special coin. It's an entangled coin. The head and tail of the coin are entangled with each other. Okay, there is no such thing as magic coins, as far as I know anyway. And so Marie says, okay, fine, let's get scientific about this. She goes over to the cabinet, and she brings out some spins. Gives one to Albert, keeps the other one for herself. Says, okay, Albert, tell me, is your spin pointing up or down? Albert says, it's pointing up. Marie says, mine's pointing down. Repeat the experiment again and again. Albert's spin could be up or down. Marie's is always the opposite, 100% of the time. So those are electrons. Those are real physical properties. Nobody's going to tell you that they don't exist. But the thing is, these spins are entangled in the way the entangled coin is. And there's a hidden reason for it, which is that you can't consider those spins to be independent of each other. They are always found together in a state where there's a special rule, and the rule is that the spins have to be antiparallel. That's it. There's a hidden rule that nobody told you, which makes them entangled. So, okay, you don't have to believe me. Do not. And it seems pretty far-fetched. But the reason that you should believe me is that experiments have proven that this is really the case. This is just an amazing fact of nature. And so those experiments are, in fact, really at a very high level, very exquisite, very careful manipulation of quantum states. And so the area of quantum metrology deals with very small quantum states, maybe just a few electrons. In the middle is the Sycamore quantum computer. There are 53 quantum states in that system. And even if you're inclined to be doing an experiment at CERN, the particle accelerator in Switzerland, if you make top quarks, for the short period of time that the top quarks are present, they are entangled with each other. And that's for, say, millions of quarks. That all seems very, very convincing. But I've always kind of wondered how entanglement is manifested, for instance, in condensed matter systems, where you have 10 to the 23rd atoms, which is a lot more than anywhere else. And so I would just repeat that we in condensed matter physics have the advantage of we know a quantum state when we see one, and we know how to make one. We have many examples. There's that. And at the same time, we also know how to do many kinds of experiments on those systems where we know quantum states are present. The hole in our understanding is that we don't know how our measurements tell us anything about the entanglement of the electrons or the spins. Right? We can do any measurement we like. We know we have quantum states present. How do we connect those two things? And so that's what I will talk about for the rest of my talk. Okay, so I would say that an experiment on a system with 10 to the 23rd atoms is probably a lot like this kind of a system. This is a colony of penguins, I believe. And so you can see that, well, you imagine that penguins are not very organized, and that if you looked at this a minute later, they would have moved in some way. If you look at it 10 minutes later, it'll be, so there's a lot of penguins there. There are a lot of ways that you could organize those penguins, right, to different kinds of states. A lot of ways. And so I'm going to use this example of the penguins to try to build a model of a regular material. So I asked each of the penguins to hold a spin. I ran out of patience in giving them spins, but imagine they have them. And so the question I have for you is that if you're thinking about entanglement, sorry about that. Is it these guys who are entangled with each other because they're standing right next to each other? Or is it possibly this guy and that one back there that are entangled with respect to each other? And of course, the answer is yes, that must be true for all the penguins. And so I'm going to impose a little order on the penguins. I'm going to, do penguins and dogs get on? I'm hoping there's not a problem here. So I'm going to ask the penguins to stand on this lattice. And so this is how the atoms are arranged inside a real material. And so we have an electron with a spin on each of the vertices of this lattice. And the blue ovals represent the entangled state that you already know about, where these two penguins, maybe their names are Albert and Marie, I'm not sure, can arrange the spins between themselves in these two ways. And I'll represent this state, which is an entangled state of the spins by these blue ovals, which show that the two neighbors are entangled with each other. So this is one level of entanglement in the solid, but there's another level as well, right? Because there's all these configurations. Penguins do not hold still. So even if I put them in this configuration initially, they're going to end up, talking to their neighbors, maybe walking around a little bit. So the configurations are changed. Many, many, many ways we could organize penguins. And so it's all these configurations together. There is a entanglement associated with all these configurations, and there's a different entanglement which happens at the shortest length scales. And so this is the quantum state, a representative of a quantum state that you might find in a real material. And so, like the entangled coin, if I say, okay, do a measurement and tell me what the answer is, you'll get one of these configurations. This is like a coin that has many, many surfaces, not just heads and tails. Okay? So that's my best shot at telling you what an entangled state would look like in an actual material. And given that I'm going slower than I thought, I'm going to pass on this, other than to say that we can also do experiments that will give us information about how the spins are organized inside the material. And that's going to provide us the experimental insight. And essentially sorry about that. Essentially what we do is we put in a neutron and we induce a spin flip which destroys one of those singlets. Okay. And so here is the actual experiment. And it's called neutron scattering. And so we begin by having a beam of neutrons, which is provided by a nuclear reactor or possibly an accelerator-based source. Those neutrons have known energies and momenta. So they go into the sample, they interact with the spins inside the sample, and when they come out, they are now at different energies and momenta. So you can think of the neutrons that come out of the sample as being like a negative of a photograph. They give you an image of what's going on inside the sample. They are not identical to it. However, we can reconstruct what's going on inside the sample by placing a detector so it catches all the neutrons that are coming out. And this is an actual picture of what that detector looks like to give you some idea of scale. Each one of these sort of stripes is actually a detector. And if we choose one of them, what we're going to see is that the neutrons that come out have different energies, and they'll have a favorite energy, such as I indicate here. And if I then look at all the detectors together, I get these patterns as functions of energy and momenta. And And that is, I think, what I need to say about the experiment. So my next slide, I will show you the experiment. And so this is really it. So the material that's being studied is this one, potassium copper fluoride. It's got chains of copper atoms, as is indicated here. And the question is, are the electrons associated with those atoms entangled? Well, stop. That's the question. So we do the neutron scattering experiment, and we get a pattern that looks sort of like what you saw on the last slide. It's a different material. And you say, great, the experiment worked. So then you go down the hall and you talk to your friend, the theorist. You say, I need to know something. You need to tell me what the quantum states are that are responsible for this. They're like, anything for you, Meigan. And so they go away and they try all their quantum states that they know about. And they come back and they say, we found a really good match. We found a set of states that looks just like your experiment. You say, we're done then. And so now you say, well, okay, I see that there's an experiment theory handshake. That we brought those two pieces together in a way we hadn't done before. What about the entanglement? And so we're very close. What you can do to deter is there's a property called the quantum Fisher information that I will not belabor. But imagine this is your computer screen at home, and you know when you bought it, it said there's a certain number of pixels in this direction and in this direction. Okay, so I just want you to count up the intensity in every one of those pixels. You'll have a big long Excel spreadsheet, and at the end you'll get a number, right? And you can do it for the theory as well. Just going to get a number. But does it help you if the entanglement is a number? I'm going to say not so much, right? I never thought personally that it would be a number. But if you repeat this process at different temperatures, you can plot it as you see at the bottom. And you can see that this number, the quantum Fisher information, is about 0.3, let's say, at room temperature. And when you lower the temperature, it gets as big as 2. And so once again, great, the entanglement is 2. I can rest easy. But actually, these numbers have meaning. And specifically, if you find that this number is less than 1, it tells you that the configurations of the penguins, if you like, or the electrons, there is no entanglement. And so these are essentially free electrons. However, you get down to lower temperature, and you have a information which is bigger than 1. And in that case, only pairs of configurations are entangled. And at the lowest temperatures, you approach 2, which would be your signal that groups of configurations which are 3 or more can become entangled. So this does have a direct bearing on the entanglement. It is a measurement of entanglement for a particular system. It is not the only measure of entanglement that we have, but I think that this is, among others that we talked about in our conference this week, this is really a major step forward for us. To be able to quantify entanglement in this way in a condensed matter system. So to just conclude, one could start with a picture for a phase transition which is quite minimal, which would be if you started with the phase, and this is, I apologize, these two slides are another analogy. We start with phase 1, which we can measure to be phase 1 because it's red, and the phase transition does something to it, and there are these additional phases 2, 3, and 4 that occur, and we know they're different from phase 1 because they're different colors, and we're measuring colors. And so this is a pretty minimal picture of a phase transition. Knowing about the quantum states, about features of quantum states such as their entanglement, add a real richness and depth of understanding to the phase transitions. And so, for instance, we would know, that it's not red, but the red phase 1 is actually a red sports car, and it's entering into some of you from the UK may recognize this roundabout. It is a magical roundabout, so it has magical properties. And you may come out of this roundabout transformed into somebody on a horse. Maybe you're riding a motorcycle, or possibly you're driving a tractor trailer. And so knowing this additional level of detail will really help us to better understand the properties of the phase transitions that provided these transformations. And so with that, I would simply like to thank all the people who have worked with me in recent years on this project, and thank you very much for your forbearance. Would be happy to address any questions as long as they're easy ones.
It's not easy, but I'm curious what, if any, kind of metaphysical insights you take from your work.
So the question was whether I would take metaphysical insights from this. And I assume that you mean something about action at distance and linkages between objects and people. Can you clarify?
Anything about the way reality works that we didn't understand before that has larger implications?
So you're probably a physicist, because I would say that that is pretty well the idea that animates us, which is that we wake up every morning, knowing we don't know very much, and we try to do our best to understand some aspect of it. So, of course, I don't really have an answer to your question.
No.
Tune in later.
Thank you.
I was going to ask, are these states of matter similar to chemical and physical allotropes? And in the various forms of like helium, like the observation of like helium-2 and complete elimination of viscosity that was found in the 1960s. And then going further, and the various energy states of electrons, which is part of like what this seems to be going into. This is maybe a stretch, but when there's like a volcanic eruptions, not really explosions, there's a change in the phase state change. And so if you have like a shock, what you showed where you delivered into the supercooled water, that there could be a rarefaction, if you will, reduction and localized that could cause a lifting, and thereby more material is released until there's minimal energy left. And just curious as you see any linkage there.
So that's okay. So I'm guessing you're a geologist.
I'm just a geek.
My kind of person. So the question was that several examples were given of different systems with phase transitions in very different sorts of settings. The first question is, what are allotropes? And so allotropes, for instance, when I showed you the iron phase diagram, there was alpha iron and epsilon iron. They're both 100% iron atoms, but the atoms are arranged in different ways inside the crystal. They are two allotropes of iron. And so, indeed, the crystal lattice and its properties and its symmetries, drive a large number of the properties of the materials that we're looking at. We also mentioned superfluid helium-3, and indeed, that is an intensely quantum phase, and it is. Does it have a quantum critical point? Chandra Varma would know the answer to that question. I don't know that it's discussed in those terms. It's discussed as an individual phase, and I think that perhaps that was one of the points of my talk, which is that the phases are connected. That there's a continuous thread through them. As you change things like pressure and temperature, you can get different phases, as you've suggested. And I think the last that you suggested actually has to do with continent formation, right? With the basalt granite transition. These are two different. They're not crystalline phases. They're rocks, but with variations in temperature and pressure, the composition of the minerals can change, and the light one goes up and the heavy one goes down, and that's related to continent formation and such.
So the follow-up to that would be, so if you're going into black holes, mergers, and so forth, the release of gravitational waves, do you see any connection in quantum fluctuations, maybe localized, from a change from energy and mass and time and space as possible expressions of the same thing?
I'm really not qualified to talk about that. I think that's more in the realm of high energy physics or possibly astrophysics. Sorry for that. Would anybody else have another question? Sure.
One of the questions I always seem to get is with quantum entanglement, why can't that be used for communication?
So the question is, why isn't quantum entanglement used for communication? And so I believe that that is an open topic and that it's being studied. Again, it's sort of by those quantum metrology people that they have very minimal systems where they can control things to an exquisite degree. This isn't the situation in condensed matter physics, where we love a mess. We think more is different. So could it be that quantum materials could be the basis of some technology like that? I don't think I'm going to live long enough to find that out, but maybe. I hope. I don't know. It's plausible.
I'm not even sure how to ask this question, but if quantum states are conditional, is entanglement a permanent state? Once entangled, can they become unentangled, the particles?
Well, absolutely. The slide that I didn't show you was sort of a scheme for how that would happen. So essentially, if you had two electrons, Albert and Marie, and you caused one of them to flip the spin, but not the other one, okay, you could break that entanglement. And so you could remake that entanglement if those electrons, paired up in such a way that you also have just up and down electrons together in some other way. And so you're right that a central feature of quantum systems is sort of their fluidity, that you have all these configurations and you have quantum states that depend on those configurations, and they're constantly being changed just because of the overlap between the states. You don't have to absorb or give up any energy. The states are always naturally entangled with each other because of that overlap. So you're dead on with that question. Sure.
Does quantum entanglement bring into question the light speed constant?
I'm sorry, like what?
The light speed constant, does it bring into question?
I'm afraid I don't know.
Well, you've got entanglement, something's happening between two particles, and they can be very distant apart.
Mm-hmm.
But
I see what you're saying. And so the question is, for instance, if Albert and Marie were on spaceships and they went apart from each other, and then, they decided that they were going to look at their spins at a certain agreed upon time. And so they do this, and then they would have to send communication to each other using light, let's say. That's the fastest communication that there is. And only at that time would they be able to compare their results. But you would still have the same result. So you could say it was, perhaps that the spins aren't allowed to flip, during that voyage. You put it in an envelope, and it was just the same as it was when you left the Earth. And so you don't actually have to communicate between the two spins for them to be entangled in that sense. It's not a natural sort of, situation. And that's why I said that it's one of the things that actually has to be measured. And if you trust the measurement, then you have to come to that conclusion. You don't have to feel it in your bones necessarily.
So my interest is in applied quantum biology, and I was wondering if you could speak to, if you know about Gerald Pollack's theory about the fourth phase of water, exclusion zone water, or easy water. It's like a highly structured, negatively charged, what he calls the fourth phase of water. If you know about that, or
Sorry, I don't.
I think that's all the time we have. Can we all give Meigan?
Thank you so much.